guys! After much fanfare, we have finally finished our previous unit on the applications of derivatives, and I've been hyping up the fact that we would start a new unit on integrals. Namely, we start this with today's section on antiderivatives and indefinite integrals. Well, what the heck are both of these? They're new terms for us. Let's go ahead and see if we can start off with an introductory example to give you guys a taste of where we're going thus far, at least if I can get my pen straight here. Okay, so example number one, and this is going to be kind of a different question from what we're used to. If f prime of x is the function 3x squared, what is f? This is a little bit different direction than what we're used to doing, right? Typically, I give you guys some sort of a function. I ask you guys for the derivative. We've seen a number of different sections previously that you can use that derivative to then do things or obtain information. Here I'm asking us to go backwards, right? I'm giving you guys the derivative, and I'm asking for the original function instead, which is a little bit strange. Now, most of you are probably like, well, this is easy. If this is my derivative, then probably f of x equals, if you're really up on your power rules and comfortable with going backwards and forwards here, we probably started with a cubic function, right? Power rule says if this is my original function, to derive this, you bring the 3 down, you subtract 1 up top. That would give you the function 3x squared. Now, I will note that this guy is a possible answer. Why is it just a possible answer? Well, we've got a couple other options here. What if I thought of the fact that when you derive constants, you get 0? This means that any constant that I wanted to throw onto the end of this would also give me a similarly working answer. That means I could say something like x cubed plus, 6,000. This is an option. So is if I wanted to do something like f of x is x cubed minus pi. We're going to get a whole bunch of options here. So first off, I wanted to make one possible note. Depending on the situation, and we'll raise a couple practical examples later, it may be useful for us to, take a reverse derivative, right? This is kind of what we're doing here. We're taking a derivative in reverse. In other words, what I mean is, instead of actually taking the derivative, we're asking what function we started with to get the derivative that we have. Hence, this is what I'm calling an antiderivative. This is my formal term for what I'm calling this process here, where you are given a derivative and you are asking for the original function. Start with f prime, ask for f, instead of the other way around. Another observation that I will make here, once we have taken an antiderivative for a most general and most applicable to all situations antiderivative, so for a most general antiderivative, we are probably going to have to be very, very careful about my constants that go on the end. Okay, so this is just a taste of what we're getting into. Let's see if I can move over to my next slide to kind of formalize this a little bit, right? If you want the formal definition, the formal theorem statement of those observations that we made on the last page, this is it right here. I've got that, my capital F of x. This is called an antiderivative, just like I introduced the terminology on the last slide. This is called an antiderivative of little f of x on an interval if capital F prime is the same function as little f for all x in the interval. right? And I can flip back to the last slide really quickly just to double check that this statement is true. Does capital F prime equal little f? Well, let's ask this question again. Does capital F prime, or, these are all of the functions that I'm viewing as capital F prime, does the derivative of those guys equal, well, if I wanted to shift my title over here, let's, think about this guy as F. Do the derivatives of all of these things look like this guy? Well, sure, right? When you derive, the constants fall off the end, and you're going to get the function 3x squared. So sure, that makes sense in context of being an antiderivative, right? Even though the names of the functions are a little bit different, right? So capital F is called an antiderivative of little f, if we derive it to get the original function back. A comment here in this notes that, remark that we made about throwing a constant on the end. If we were looking for the most general antiderivative of a given function, you are going to want to make sure that you slap a plus c on the end, okay? And we assume that this plus c is going to be some sort of an arbitrary constant. I'll give you guys an example. Let's see if we can click over the next slide here. If little f is cosine of x, find the derivative or the antiderivative of little f of x, right? So basically what we are looking for here, what we want is a capital F of x such that capital F prime looks like little f. So really the question that I'm asking here is, what function did I have to derive to get little f equals cosine of x? Now, if you're comfortable enough with your derivative rules, the function that you take a derivative of to get cosine is the sine function. This is going to imply that my capital F should be the sine function, because, you take a derivative of this guy, you take f prime, capital F prime, and you get cosine of x, right? Now, this is not quite a full answer for this question, because of that silly theorem that we just mentioned on the past page. If I throw a plus c on the end of this, that is going to give me a more general response that works in all cases. I don't know if I started out with a constant before. I could have a plus 5,000 on here. I could have a minus 10. I could have a plus e. Who knows what's on the end of this thing? But if I want the most general answer, if I want the antiderivative for little f of x, not just a antiderivative for little f of x, this guy is it right here, right? And we can double check that this actually fits the criteria for being an antiderivative, because does its derivative equal little f of x? Well, let's think about it. If you derive sine of x, you get cosine, sure. If you derive c, well, it's a constant, so that drops off. We've just shown that my derivative of big F matches my original function, so sure, this guy is my antiderivative. Now, some comments on this. Note number one that I will make for you guys. I was really harping on the fact that we had that plus c on the end. If you are asked to find one of these antiderivatives, always, and I'm going to write this in big capital letters, include your plus c on the end. Every time. Reason being, unless you are given any more information, you can't guarantee that c is 0, right? We don't know that c is 0 without more information, or unless we are specifically told that it's 0. So if I'm looking for a general cause, or if I'm searching for some sort of general application for this function that I'm investigating, maybe we don't understand the applications now, but we will see them later. If you want to find an antiderivative, assume that there is going to be a plus c on the end. Always, 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 always. Note number 2. Second comment that I will make about my notation that I am using here, because I did sort of flip between my initial example and then the way that we've talked about the definition of the antiderivative. Here, my capital letter F. Okay, so capital here, if it's not obvious with my crappy handwriting. F typically denotes my antiderivative, the antiderivative of the function little f. This is not the only situation that you would think of, an antiderivative for a function. We also have that if we are already currently expressing things in terms of derivatives, kind of like I did on that very, very first slide, we also have that f is thought of as an antiderivative of f prime. And you can kind of go a little bit deeper down the rabbit hole here. F prime is an antiderivative of f double prime. F double prime is an antiderivative of f triple prime, etc. Right? The whole idea of a function being an antiderivative is, can you derive it to get the function that you started with? So, if I'm saying that f double prime is an antiderivative of f triple prime, what that's assuming is I was asked to find the antiderivative of f triple prime in the first place. That means if f triple prime is the function that I was given in the first place, what do I have to derive to get there? Now, rather than resorting to capital F notation, the thing that you derive to get to the third derivative is the second derivative, so we'll write it as such. Similar comment down here, if I'm looking for an antiderivative of the second derivative, I am asking what did I derive to get here? Well, you derived the first derivative to get there. Same deal up here. What do you derive to get to the first derivative? The original function. Here, since there's not really a name for what goes beyond little f, this is where we stepped in and we had to come up with something. This is why I introduced that capital letter notation, capital F. So we're assuming that the thing that you derive to get to little f, that's the capital letter. And I will go ahead and make a comment. It is common to extend this idea to other letters. We don't always call our functions f. Sometimes we call them g, sometimes we call them h, etc. So we can extend this idea to things like, let me write the correct character here, g, h, etc. So if I was asked to find an antiderivative of little g, I might say big G. I might say that the antiderivative of little h is big H. Okay, so we use a similar notation there. Another final comment that I want to make on the antiderivative, and I will scroll down to give myself a little bit more room here. Another notation for my antiderivative. Okay, so I'll specify for the antiderivative of a function, little f of x, and I will specify with respect to the variable x. So I am naming and really reinforcing that my independent variable is x here, is the following. We might just say the indefinite integral of f of x with respect to x, right? So basically the whole purpose of this is I could say something like find the if I could spell, antiderivative of the function little f of x. Okay, oops, let me erase that here and actually finish my quote properly. I could say that expression, or if I scroll down here, this is the same exact thing as me saying evaluate this expression. You will notice there's a lot more characters in this sentence or this expression than there are in this one. So this is a shorthand, lets us, give instructions on what we're computing a lot faster, right? If you guys see this little squiggle here to the left of the expression, that guy is called an integral symbol. This little differential dx on the end, it just reinforces which variable you're working with, and it kind of gives a cap on the expression to tell you, where does my function stop, right? What thing am I actually finding an antiderivative of? This is a begin marker, this is an end marker, and it serves as, what I've referred to a couple times in this class, as an operator. That pair of symbols is the thing that gives you an instruction on what to do, right? So basically, these symbols here, okay, with a thing on the end, these guys are an operator. Let's say, take the antiderivative. Okay? So, in other words, if I wanted to give you guys an example, and I will scroll down here just a little bit, we could rephrase that example that we started out with. So I will continue that example. If I wanted to find the antiderivative of 3x squared, since this guy is stuck in between those symbols, we have already discussed the fact that x cubed is the thing that it looks like you derived to get to 3x squared. We've already discussed the fact that for the most general antiderivative, you want to throw a plus e on the end. This is just fancy notation for me to say, hey, take the antiderivative of this thing right in the middle here. That's all it is, okay? So, as a note, that set of symbols, so I will kind of close this here, my final note on this section, anytime that I see something of this form, this guy is called an indefinite integral. Okay? Indefinite integral. And if I want to be specific what I'm taking the indefinite integral of, this is an indefinite integral of f of x. Okay? It basically evaluates to the antiderivative, capital F of x plus c. Okay? I guess if you want to, be specific here, and I can write the, that's fine. This is the indefinite integral of f of x. Now, we've got some of the terminology down. How about computing some of these, now that we know the language and the notation for dealing with these expressions? Well, I'll switch us over to the next slide. I've got a few antiderivative rules here. Okay, maybe you might balk at the fact that I'm saying a few, and I've given you this gigantic list. However, I'll make a couple comments about this list. I've got these functions over here on the left-hand side and their corresponding antiderivatives over on the right-hand side, but if we look super, super close, you might recognize a lot of this is stuff that we should already know in the first place if we know our derivative rules, right? Since the point of the antiderivative is that I take a derivative of those functions to get back to these originals, well, we're really doing our derivative rules, but in reverse, right? Over here I'm thinking, what function do I derive to get the constant k? Well, Anytime you derive a kx function, you lop off the x and you keep the k. What function do you derive to get the exponential? What function do you derive to get 1 over x? What function do you derive to get cosine? Okay, these are all basically our derivative rules, but I'm just asking you to literally know them backwards and forwards, right? Not just take the derivative of this function, but I am also asking you to know what function did I derive to get here, right? So I will make a comment. This is not an exhaustive list of all of the antiderivative rules that you are expected to know. Since at this point in the class, you are expected to know your derivative rules, you should actually know a lot of these antiderivative rules off the bat. The ones for this constant here, the exponential and log antiderivatives here. I'll note that even though I've only included 2 of the trig functions and 1 of the inverse trig rules on this list, these are not the only ones that you're expected to know. You should actually know all, okay, of your corresponding trig and inverse trig, derivative and antiderivative rules. So I will keep that in mind. If you're a little bit fuzzy on those, unfortunately in the Chimera book there's not really an antiderivative rules table. What I will reference here, if you want a place to go to that has all of these in one list, basically see, Chimera section 2.10. This was the official list of all of your derivative rules in one spot. Basically just look at this and think of it backwards, right? If you want a list of your trig and inverse trig antiderivative rules, just look at the derivative rules for those trig and inverse trig functions and just think about them backwards, right? Minor caveat here, be really, really careful when you're paying attention to those signs of those trig and inverse trig functions. Some of them came out negative, some of them came out positive. So there are a couple sign switches there that you should be very conscious of. Namely, if you're anti-deriving and you're expecting to get a function back that starts with c, expect there to be a sign change, right? So if we anti-derived sine and we got a cosine term, well, that was a c function. There needed to be a sign change in that. This is kind of the analog of us saying that the derivative of all of those c functions was negative, okay? Now, you'll notice I listed a bunch of these, but there's a couple things that are conspicuously absent. Namely, my power rule doesn't show up here. There's also a general exponential rule. That doesn't show up here. Well, reason for that is there are a couple less obvious rules for us. Now, the reason that these were different is we're trying to undo the derivative, right? Now, if I really want to break down what's happening in these antiderivative rules, let's think about this power rule one first. Now, the derivative power rule has me bring down my exponent as a product. Now, if we're trying to undo my derivative, I don't want to multiply by that constant. I want to divide by a constant instead. So this is why we're ending up with this bit here down in the denominator, right? The n plus 1 that's popping up here. Now the next thing that we're going to do if we're applying a derivative rule for power rule is after bringing down the constant, you subtract 1 up top. Well, if I'm looking to undo that, instead of subtracting 1 up top, I want to add 1 up top. So this looks a little bit strange compared to what we're expecting for a true derivative power rule, but if we consider the fact that we're trying to undo the derivative and that we're performing these inverse operations, hopefully this makes sense. I can make a similar comment if I'm trying to figure out the antiderivative rule for the general exponential function. My derivative rule for that is basically copy over the function and multiply by natural log of the base. We're trying to antiderive. We need to undo that. So if I'm undoing multiplying by log of the base, well, to undo multiplication, you divide. That means that you're going to divide by log of the base. Okay? Now, a couple comments on these little side restrictions that I have next to these rules here. First off, your general exponential function, we only ever work with that when we're dealing with positive constants on the base. So that's what that restriction's about. This one up here, if we think about it, we can maybe see why this is a common sense restriction. When n is the number -1, that means I've got x to the -1 power. Another way to rewrite that is 1 over x. So basically what this restriction is saying is don't apply the antiderivative power rule when you should be applying the log rule instead, right? The antiderivative of 1 over x should turn in natural log of x, not some power rule term, okay? So some comments just on usage of these guys. Note one that I probably should apply here if I'm thinking about my my exponential terms. One, if I get my pen straight here, if I want to apply my power rule, please make sure that your expression is in the form x to some sort of number, right? So I'll draw a parallel between here and when we were working with derivative rules. There's all sorts of derivatives that we can take using power rule, like roots and 1 over x to a power. There's all sorts of those to apply the derivative power rule. We needed to write it in this form. Well, it shouldn't be so crazy to expect that if I am seeing, something that undoes one of those rules, it might have to kind of play a similar game. So if you're applying antiderivative power rule, or if you're looking to apply antiderivative power rule, make sure your expression's of the right form. A second note that I'll go ahead and make here, just to really reinforce this. I mentioned this on the last slide, but please be careful with your signs of your trig functions, right? Anytime that you antiderive and you expect to get a function that starts with c, expect to see a sign change of your antiderivative, right? Let's see if I can try to apply some of these. An example. I'm giving you a function little f. I want to find a big F. That means I want an antiderivative of this little f function. Okay, well, side note number one, the last slide, I gave warning. Anytime that I want to apply antiderivative power rule, I'm probably going to want to rewrite my function. So I'm not applying an antiderivative just yet. I'm just doing a rewrite step. That first term looks like something that if I wanted to do derivative power rule on it, I would have to rewrite. So if I want to do antiderivative power rule, I have to similarly rewrite it. We can also think of this function as, if I fix up that first term, this is really x to the -1/2. Notice I am not actually taking the antiderivative yet. I am just rewriting my original function f in a more convenient way. First off, we view roots as half powers, but it's in the denominator, so I can flip it up to the top and making it negative. Okay, so I've got a nice rewrite here. Let's see if we can work on finding my capital F of x, or my antiderivative. What my rule said for power rule, right? And I'll write this just as a refresher here. Your antiderivative rule for x to the n, this was supposed to be add 1 up top and then divide by that same number, right? So let's see if we can do this with this term. I want to add 1 up top, so I have x to the minus a half plus 1, and then I want to divide by that same number, so I'm dividing by minus a half plus 1. For my next term, I need to antiderive this 6 here. Well, what do you derive to get a 6? Well, you probably needed to start with an x attached to it. That was 2 slides back. And then for this term that's on the end, if I'm worried about anti-deriving this cosecant squared term, I have to think about what do I derive to get cosecant squared? Well, you derive a cotangent term to get a cosecant squared term, but like I've noted on the last slide also, we get a sign change, right? So I should expect, since I am ending up with a cotangent term, and that's a C term, I expect to see a sign change here, right? Now, I can go ahead and clean this up, right? So I will, simplify this here. I am getting x to the basically 1/2, and then I'm dividing by 1/2. Over here, I can just think of this as subtracting cotangent. If I really want to tidy this up and give it a final polished spin here, first off, dividing by a fraction is the same as multiplying by a reciprocal, so I've really got a 2 as a coefficient, and x to the 1/2 is really the same thing as the square root of x. So this should be, pretty close to a final version of my function. One thing that I will note, that I'm going to throw onto all of these here, for my most general form of the antiderivative, what do we need to do? Please make sure that you've got a plus c on the end. Okay, so this is something that we can tack on here for a general antiderivative. Now, as comment, if you are ever concerned that you have taken an antiderivative and you aren't 100% certain if it's right, a thing that you can do to check, what you can go ahead and do is take your derivative of it to see if it works, right? So here, if I wanted to double check this, right, see whether or not this works. If I want to derive this, what I'm going to get is, hang on to the 2. This is really a power rule term next to it. I have x to the 1/2. This is going to turn into 1/2 x to the negative 1/2. Over here, my minus 6x will turn into a minus 6. And over here, my derivative of the cotangent function is negative cosecant squared. Okay? And finally, my derivative of constants is going to drop off. Now, if I think about what this simplifies to, well, let's compare this, right? First off, my 2.5 are going to cancel. I am just left with x to the negative 1/2. Hey, that's the first term of my f function. Similar deal here, my minus 6 shows up again, and here I was subtracting a negative cosecant squared. That shows up in my f function. We get exactly f back once we derive, okay? And what that shows is that we derive and get f, my original f, if we did it right. And, since it matched, hey, we actually did it right. Okay, so this guy, this is our antiderivative that we were looking for. Now, don't want to be a downer, but some more rules for you guys. Some of these are actually ones that we've made use of on that last slide because I was really heavily hoping that we understood our derivative sum and difference rules enough to be able to apply this readily in that last example. First off, your antiderivative of a function that has a coefficient to it, just hang on to the coefficient and antiderive the function, right? it's kind of the same idea as derivative constant multiple rule. Whenever we derive, we hang on to the constant coefficient. So it should work the same in the other direction. Similar deal with derivative sum rule. If you're deriving a sum or difference of functions, you kind of hang on to each of those sums and differences, each of those plus and minus symbols, and then you just derive the pieces. Okay, that was exactly what we did in the last example, even though I didn't come out and say that we could do it first. The one thing that is, kind of something that we should watch out for, that maybe doesn't initially behave intuitively, we don't currently have rules for other products and quotients, so anytime that I run into a product or a quotient, I am going to have to rewrite it so that it's expressed purely in terms of sums and differences or constant multiples. Okay? We don't have rules for products, we don't have rules for quotients, we don't really have rules for compositions either, right? All of those special things we're going to need to rewrite. So the parallel that I'm going to draw here to really beat this in for you guys, we needed special rules for those in the derivative case, right? We need special rules to derive, products, quotients. I didn't really write this up here, compositions are also included. So we needed special rules to derive my compositions. You are going to also need special rules to undo them, right? So it's not just that it works in the one direction that you need special rules to derive. Any case that you would have needed a special rule to derive, like product or quotient rule or chain rule, if you see similar functions and you want to antiderive, we're going to need special rules for that too. Now the catch is, a lot of those don't come until Calculus 2. So if you were worried about facing that now, you got a little bit of time. But do keep in mind, anytime you see a product, anytime you see a quotient, anytime you see a composition, at this point in the semester, since we haven't built all the other stuff in our toolbox yet, you're going to have to simplify it to get rid of that stuff. Okay, so here's an example of what I mean. Let's say that I want to evaluate the indefinite integral of this product. Right, now remember, this was just a fancy way to say I want to take an antiderivative of this function. That's it. Now, it's a product. I can't antiderive products of functions yet. But what I can do is I can rewrite it so it doesn't look like a product anymore. If you actually FOIL this out, you get 2x squared for my first. My outer is minus x. My inner is plus 2x. And my last is minus 1. Here, I can stand to do one more line of simplification. If I clean up my like terms, I'm going to get a plus x in the middle. This is now something that doesn't have any products in it. So I can treat this like sums and differences and constant multiples and go ahead and carry on through and do my antiderivative rules. Right? So I'll go ahead and try to tackle this. First thing I run into has a constant coefficient. Much like derivatives, we hang on to constant coefficients. The next thing that you have to do is just deal with the rule for the thing that's attached to it. Right? We're antideriving x squared. Now the way that that worked was antiderivative power rule says you add 1 up top and then you divide by the number. So rather than bringing the number down as a coefficient and subtracting 1 up top, we're doing the opposite. Okay? We are adding 1 up top and then we're dividing by that same number. Okay? Similar deal over here. It might not be obvious, but this is a case that you have a power of 1. So if I want to antiderive that, again, I add 1 up top, and then I divide by the same number. Over here on the end, I have to think about what function did I have to derive to get 1? Well, that should have been x. And if I want to finish this out, since it is an indefinite integral, since it is an antiderivative, and I want the most general answer, we always have to throw a plus c on the end. If you want to rewrite that front coefficient as a 2/3, you can. If you want to leave it as is, you can. Okay, both of those are going to be acceptable answers. Now, a comment. Do you ever get to know what that c is on the end? I've been really harping on keeping the c on the end, but what do we do with it, right? What's the point of it? Well, we only get to know what it is if I have more information that's given to us. And problems of this sort are called initial value problems because I am specifying what that c is by giving you clues that'll let you find it. Right? So here's an example. I'm giving you guys a derivative. I'm asking you guys to find the original function. That calls for finding an antiderivative. Right? So in general, we are going to expect, okay, expect to antiderive to find my y, right? We should get that y is the antiderivative or the indefinite integral of that function, right? This 3e to the x plus 1 over x dx. The dx is just there to cap off and tell me where my function stops. Okay? So if I'm looking to antiderive this, what function do I get back? Well, again, constant multiple rule says we hang on to constants, and then I worry about antideriving the thing next to it. Well, what do you derive to get e to the x? That's a boring function. It's just e to the x. Sum and difference rule says we're going to tackle this piece by piece while hanging on to our pluses and minuses if we have any. And then I hit this 1 over x term. What do I derive to get that? The good old natural log of x function. Now again, since this was an indefinite integral or an antiderivative that we were taking, we have to throw one of those plus c's on the end. Okay? So this is my function y. But I know that this happens. If I plug 1 into this function, it says I get 0 back, right? So I'm going to scroll down to give myself a little bit more room. What this says is I should be able to plug that input value, x equals 1, into this function y and get back, spelling here, get back an output of 0. So if I pair that information with this function that I just found, okay, what this is saying is if you plug 1 in for x, right, what that looks like is this, 3e to the 1 plus natural log of 1 plus c. This little bit up top says that when you substitute 1 into the function like we just did, what this should spit back out is 0. So let's go ahead and make that conclusion here, right? So now I can focus on this beginning bit. Basically says 3e plus natural log of 1 is 0. So plus 0 plus c comes out to 0. What this is going to tell me is, well, if I solve, c is negative 3 times the constant e. So at this point, I will scroll down just far enough to give myself, some room to write my final answer. What I'm pairing is the fact that I know what my function looks like. We got it here. I know what my constant is now. If I am asked to find y, I can just pair those bits of information together, right? So my final answer for what my y is, I don't have a mystery y with an unknown c. My final y is given by the following. I have 3e to the x plus the natural log function plus, we said the constant c was supposed to be on the end. Well, instead of saying plus minus 3e, I may as well just say minus 3e. Okay? That guy, that is going to be our final answer for this question, right? So if I was looking for y, this is it right here. As far as a more practical application of this, because I know y'all are saying, okay, why are we doing this backwards? What's the point? Physics is a prime place to go looking for applications for this. In this problem, I'm naming for you what acceleration due to gravity is on Earth. It's a constant minus 32 feet per second squared, maybe a couple decimals on the end, depending on how many significant figures that you care about. But for our approximations in this class, minus 32 feet per second squared is a pretty good estimate. Projectile shot upwards at 16 feet per second from an 8-foot platform. What is my position function? Now, a comment on how to solve this thing. Based on the information that we know thus far in class, we know that if you start off with a position function and you take a derivative of it, you get the velocity function. Now, if you go a step further and you take a derivative of that, what you're going to get in turn is the acceleration function. Now, here's the catch. If we go in this direction, this is where I have asked you guys to actually derive, to go from top to bottom. Now, on the other hand, if I wanted to go in the opposite direction, well, we said that the name for the opposite direction is taking my antiderivatives, right? So we antiderive to go the other way. If I'm looking for a position function and I'm given initial information on velocity and acceleration and maybe other info about my position, I should be able to find it, right? So here's what the problem is stating. If I note that my acceleration due to gravity on Earth is this constant function, we are basically given, or we should be able to know, my acceleration function is minus 32. We are also given that my projectile is shot upwards at 16 feet per second. What this is telling me is my initial velocity, right? So at time 0, when I launch this bugger off the ground, plug in time 0, get how fast this thing is going. I plug in 0, I should be able to get 16 back. Another comment that I will note here, since this thing is coming off of an 8-foot platform, that again gives you some hints on what's going on at your initial time. At time 0, where are you? You're on the platform, right? So you're 8 units off of the ground. So basically what's being asked for here is start with acceleration, antiderive to get velocity. You are going to need that initial velocity to complete your function. Antiderive to get to position, and you are going to need that initial information on position to complete your function. Right? So let's actually scroll down and get some room to do this here. Right? What I just said. Velocity, if I'm paying attention to my chart, velocity, you derive to get acceleration, you antiderive to go in the other direction, right? So if I want velocity, I have to antiderive the acceleration function, right? So here's my a of t. This time we're in a different variable. Instead of dx, I will write dt. So here, this basically says antiderive minus 32 to get a velocity. Now, what happens if you antiderive minus 32? Well, what did you have to derive to get minus 32? Probably minus 32t, because we're working in t this time, right? We also have to throw in that constant of integration, and here what that says is my velocity function equals this. But I also know my initial velocity was supposed to be 16. So there's two ways I can compute my initial velocity, okay? We know that v of 0 is equal to 16 because this was given information, But we also know that v of 0 is minus 32 times 0 plus c. You can get this by plugging in, right? If I set both of these things equal, 16 is equal to minus 32 times 0 plus c. This gives me an obvious value for c that I can go ahead and use in my original velocity equation, right? Velocity, v of t, up here we said was minus 32t plus c. Well, we've got a value for c right now. This gives me a function of minus 32t plus 16. Okay? Let's see if we can scroll down a little bit to give myself some room to find my position function. Similar idea, s of t is supposed to be the antiderivative of the velocity function. Now, that is basically this function that we just found up top, right here, minus 32t plus 16. I will specify the variable we are working in, and then we can go ahead and worry about taking the antiderivative. We hang on to constant coefficients, and then this term here, t, is just t to the 1. So I will have to add 1 to that exponent up top, and then divide by the same number. I will continue along here. What do I derive to get to 16? Probably 16t. And I will get a constant of integration here. Now to separate it from the constant we got before, I'll call it c2. Okay. So, two ways that I can think about obtaining s of 0 here. Either I can think about what was given to me, okay, this s of 0 being 8, or I can think about plugging in, okay? So if I think about, what is given as being s of 0, and this being the same thing that happens when I plug in 0 to s of t, well, that function above basically gives me 0 plus 0 plus c2 when I plug in t equals 0. So I've got a clear value back for c2. That guy has to come out to 8. If I combine all of this into one big function, we are getting that s of t is equal to minus 32 times t squared over 2 plus 16t plus my c2, which we just said was 8. If you do not like this in unsimplified form, an acceptable alternative would be minus 16, because that's 32 over 2, minus 16t squared plus 16t plus 8. And if you actually go back through a lot of the examples that I've given you guys throughout the semester, you'll notice that a lot of our position, velocity, acceleration questions have had this minus 16t squared term out front. This is why. We're assuming that we're doing a lot of those problems on Earth. And if you start with this minus 32 acceleration and work through the problems, the antiderivatives are going to lead you to this minus 16t squared we keep seeing. Okay? So this guy, this is my final position function for this particular example. Okay? Now, what I wanted to do is not just, leave you guys sitting back, to enjoy the lesson without doing anything. I'm going to pose you guys a quiz question here that follows very similar principles to what we did in the last two examples. If I give you a derivative, okay, f prime is negative sine x plus e to the x minus root x, and I give you an initial value, tell me the original function, okay? If anybody has any questions for me, please feel free to let me know. Shoot me an email or drop by for office hours. I'd be glad to chat about the quiz. Please turn this in at your earliest convenience.